Okay, so, let's see. So, yeah, so let's see. So, tonight, let's see. So, okay, so, we'll get started now. There was some weird stuff there. But, basically, tonight I'm going to do a tutorial, that's going to, kind of serve two purposes. One, it's going to show, in general, kind of taking a time series forecasting problem and breaking it down and creating a model, etc. Number two, it's going to it's going to show how to use our time series forecasting framework and how to use deep learning on it. So that's kind of going to be the main thing. So yeah, two purposes basically. One is just showing kind of how to approach these problems, particularly ones with deep learning in general. Two is going to be showing how this pertains to our framework specifically, and the nice things we have integrated in it. And number three, I guess it's also going to show you a bit about this data set for stream and river flow forecasting we open sourced. Okay, so just to quickly clarify, firstly, our repository, and as I'll say this many times throughout the night, this is no way just limited to stream and river flows. This is one area of multivariate time series forecasting that I think is interesting. But we've used our framework on a ton of different multivariate forecasting problems. So of other users, some of them have been things like sales forecasting, COVID forecasting, wearables forecasting, basically any type of time series forecasting. Our framework supports. We also have beta support for classification, time series classification, though that's not inherently reliable. It's like very, very beta support, so I actually wouldn't recommend using if at the moment for time series classification. That's hopefully going to come later, though. So anyways, tonight I'm going to do a tutorial actually on Kaggle. We recently actually pushed part of our FlowDB dataset, not the entire FlowDB dataset. The actual entire FlowDB dataset is very large, so we didn't put all that on Kaggle, but where's that it? So yeah, but we put a good chunk of it on Kaggle, particularly some of the more recent data that's kind of interesting there. So that's definitely one of the big things on Kaggle. So basically what this data set is a very large scale stream and river flow data set. We have a paper that was published at the NeurIPS Climate Change Workshop. It was the original inspiration for our river flow forecasting repository, though that's now obviously gone way beyond that to general time series stuff. But in any case, it's a good example of doing multivariate time series forecasting because it's very large, so there's enough enough data to train very large models. And so yeah, that's what we're going to talk about tonight. And this will probably be a series where we go through kind of a couple of different streams and rivers and look at them. So yeah, tonight we're just going to first do, as I said, this isn't solely just talking about our framework, though we will get to our framework, of course, and how to use it, but we'll also just talk about generally how to approach some of these deep learning for time series forecasting problems. So that said, the first thing and what we're going to be talking about on this river, in this series of videos is forecasting the flow of this one river that's called the Big Black River. So the first question is, well, why do we want to forecast it? What kind of benefit can we get out of forecasting these streams and rivers? And so the first thing is that there's actually a very interesting thing with, I don't know if I lost the tab, but there's a interesting thing with Noaa river forecast. Noaa already does some river forecasting, but actually it's very sparse. So actually, if you look at this map, I'll zoom in on this map in a second. So I know one side's cut off because my screen's really long. But if you zoom in on this map at different places, basically Noaa only creates forecasts for the rivers that are in kind of this square, whereas all these rivers that are circled, Noaa doesn't actually have any forecast for, either because these rivers are like they're too difficult, or they just don't have the time to actually provide it. And if you look over this map, the majority of these rivers are actually circles and stuff. They're actually the number of squares is pretty sparse. So that's one. And number two, even for some of the rivers with squares, some of their methods probably aren't actually the best forecasting methods. They're based on these old, like, kind of statistical techniques that I now actually think, particularly with a lot of data, deep learning can perform. This might be a good chance to say why we want to forecast rivers at all. I mean, of course, if we're forecasting a river, we can better alert people who might be along that river about, say, like flash floods and other types of events, to get away from the river if it's expected to surge or something like that. Also, creating a good model that can forecast the river and that is interpretable. I'll get to how deep learning can actually be interpretable in a bit. It can actually tell us a lot about the factors that go into the river flow, and tell us a lot about the hydrology and even about the climate, because what we have now in the FlowDB data set is around, for at least these rivers, is 21 years of stream and river flow data. Is essentially 21 years of stream and river flow data and stuff. So over 21 years, that can tell you, a model that learns on that, it can tell you a lot about some of the climate stuff too, for kind of interpretability. So anyways, it's good to be able to forecast it but yeah, the immediate benefits are obviously being able to better, like, tell kind of what it will be and what the watershed in the area will look like, immediately informing people if there might be a flash flood. And number two, and then another big thing is just obviously, final thing could be recreation. There are some rivers people like to paddle down at certain water levels. So that's another big thing, like, for outdoor recreation. So there's a lot of reasons why you might want to forecast it. And creating a good model for some of these could definitely tell you a lot. So the one river we're going to look at primarily is this river. This river is actually probably a river not many people would actually care too much about, because it's in the very northwest corner of Maine, right along the Canada border, kind of in the middle of nowhere. But as you can see, like, the USGS has no forecast for it. And the other good thing about it is it's not dam impacted in any way, so it's more related just to the precipitation and other stuff. So that's kind of what we're going to look at here. And as I said, this is mainly just a tutorial on how to use the framework and stuff like that. So that's kind of the main thing. I think, like, most of these, they don't have. Yeah, and actually, if you look at some of the ones that do have forecasts, I mean, some of the forecasts don't look honestly that good and stuff for certain ones, and there's just a ton with those. Anyways, I'm gonna move on to some of the other things right now. Um, so, let's see. So, anyways, let's see. There also, I think there are a fair number of gauges that aren't even listed on this map and stuff. But, so one of the things we can do now is starting out with this data set from Kaggle on one of the initial notebooks I was just doing. Was kind of doing exploratory data analysis. So kind of the first step, unfortunately, even with even in a deep learning setting, you still need to usually do some exploratory analysis, because if you just there are certain hyperparameters that are going to often require you to at least know a little bit about what's going on with the underlying data and stuff like that. And if it kind of makes sense in a certain circumstance. So particularly in data science, almost any problem you start with is going to start with some exploratory data analysis of the data set and of things like that, just to get an idea of what's kind of going on with the data. And what it looks like, and then based on that EDA, then you can start to do other things. So that's kind of what we're going to do here, and yeah, that's how we'll start with. So again, EDA, it really isn't as important that you have really tight-knit code quality. The EDA is almost more for personal exploration. Of course, it's good if it starts to become analysis that actually starts to provide, say, value that you then refactor and maybe even write tests or something. But most EDA should just be done kind of quickly to get a sense of the data and stuff like that. So we'll load it. So we'll start off by loading some of these files. So the first thing I notice when I kind of load, here I load the file, is the length of the data frame altogether is about 178,433 rows. But as kind of we note in the stuff, there's a lot of missing values. So here, for instance, if we just look at the head of the data frame, this whole area, there's no cubic footage, there's no height in terms of stream height. Oh yeah, by the way, here for this, our target for the most part is going to be cubic feet per second. That's the actual discharge of the river. Height can also be important to forecast, though it's usually not as well reported by U.S. Geological Service. Also, CFS is a bit more accurate because particularly at a really high, say, flood stage, the height might start to the river might get, for instance, extremely wide, so a lot more water is flowing down with it, but it might not actually get too much higher and stuff. So there is definitely a relation between the two. If you know one and then you know the characteristics of the river, you can probably easily just tell the other. And in some stuff, and what we might actually do at some point too is do a multitask forecasting, where we forecast both cubic footage and height at once. Because in multitask forecasting, even having auxiliary tasks that are correlated can often definitely increase performance. Anyways, that's kind of the core stuff that's going on with that right now. But in any case, right now when we first sample this, it really doesn't have that much. So what we're going to do is we're going to first just, with the data frame, then drop all the NA crap. So and basically we don't want, really, because this is a precipitation driven river, we don't want any rows where your cubic footage, i.e. the discharge, is nan, or the precipitation is nan. So we're going to just essentially drop all those Na values. What happened there? Okay, I don't know what that was. That was really weird. Anyway, so we see after this we're left with about 80 K rows, which is still more than enough to probably do some deep learning. This is a pretty large data set, as I said. I'm not sure. One of these things we can look at too is like, so it looks like even after we drop these rows, we still have data going back to essentially all the way back to 2000. So we really do have a long stretch of data here, all the way from April 2000 up to 2021. So there's a lot of data to work with forecasting. You can see here, for instance, cubic footage is filled in, but height is still nan. So if we were going to train a multitask forecasting model, we would have to reduce some of this a bit, or try to fill these in based on kind of knowing what cubic footage is. But for now, we're only going to have a single target that we'll use, which will be cubic feet. So we'll worry about some of that later. So here's kind of some of my initial exploratory analysis of this with kind of EDA. I always do you do different group buys. You look at kind of what's going to be what effect kind of seasonality has over different, and how values range. So we can see, I think we can actually even plot these two. I'll do that in a cell below. But really with EDA, I'm just trying to get a general sense of what the data looks like. Yeah, that's probably not going to be that helpful of a plot because of some of that. So I'm just going to, we'll look at kind of how the CFS, the average CFS varies by month and stuff with this plot. This is annoying. See if I can open this in a new tab. So yeah, just like obviously, yeah, it's in April, kind of like around April, May is when the cubic footage in general is the highest values, because there's probably a lot of discharge from melting snow, which we unfortunately don't really have in this data set. We don't have details on the snowpack, which is obviously a big factor. But hopefully with 20 years of data, the model can kind of learn the different spring stuff. Then moving into June, July, it looks like the river dries out a lot, and then back in the fall, there's probably more precip. We can look at some more kind of graph, I guess, in terms of precip now. And precip here is essentially this P01M, which is the precipitation in millimeters. So we'll look at that. So yeah, as you can see, some of that other stuff kind of makes sense. There's, in general, you can see precip goes up in these months, in these kinds of months and stuff like that, towards the end, which kind of correlates with this rise here. Of course, as I said, this initial rise is definitely is 100% driven by melting snow and not really precipitation, as much as we can see. Though it looks like there's some precip here too, maybe. Though it's hard to tell what actually that means. You can look at some of the values, and we can always go back and look at some of the values. Yeah, it actually looks like January is like a huge month in terms of precipitation So yeah, we can. So those are some of the initial things. One of the things we can do too is just look at some of the min and max values too in the data set and look at kind of the areas in which they occurred and what maybe drove them. Um, I wish there was a nicer way to display some of these here. Yeah, probably a good chunk. Well, we'll get to actually forecasting tonight, but most of the time when you're doing data science work and stuff like that initially, you're going to probably spend a lot of time on some of this preliminary analysis stuff. And actually, we're looking to probably make some more of this preliminary EDA stuff automatic in flow forecast, so you could just like pass in the data and it would automatically generate different plots and things like that. But anyway, so kind of moving on. Go unnamed 0, unnamed POM. So what can we do here? So yeah, one of the things we can look at now is, as I said, one of the one of the big precipitation events and kind of what kind of correlation and stuff is there. So yeah, maybe it might be good to actually search by max and stuff. So we'll go back to the original DF and stuff, and we'll just do. We want to get the like row numbers and stuff of the. Almost write a query type thing. So POM1. I don't know if this will return the row. No, that just returns the max. Oh, we could. You know what you could do? You could do like something like PO1. So now that we know the max, we can just do that like equal sign or something. I actually rarely write too much SQL or even pandas queries, since I do a lot of just development of deep learning models, but this is always a good refresher and stuff. Equals, let's see, 34.04. I think that should work. Oh yeah, that should just be POM1. Should get us the row. So let's see, it looks like this row was sometime in 2009. It looks like there's like really hard rain or something. So that was in August. And we have for, what is it? So let's look at this whole block now. We can sample, say, like from a bunch of ones to there. So this looks like it's 6,053. So let's go back, say, like 25 or something. So that would be equivalent to 25 hours, all the way from 6,000. We could do it from here to 100, give us about 75 rows to see what's going on there. CFS. So here we'll look at cubic footage. Wait, that doesn't look right. No, that's not right, actually. Yeah, no. That's not correct. Oh, wait, no. This is 60,000. Oh, that was stupid. No, it's 60. So that's 60. Here we go. So here's some of the stuff. Looks like essentially PON1. Let's look at that in more detail. So we can do something like CFS. Or let's plot the percip. Maybe I don't know if it will make it look weird if we plot these both on the same thing. I know there are ways of doing it. I don't want to go in. Oh. You know what I'll do? I'll just call this something like DF percip sample. And we'll just do like DF percip sample. I don't know why it's not giving saying those are invalid. I don't know if those are supposed to be nested. Oh yeah, it's the stupid nesting. So this should actually be pandas is always this way, I think. So that's the cubic footage. There's the percip. So I don't like how that's partially covered and stuff here. But anyways, so yeah, it looks like there's a big bump in precipitation. Likewise, you see the stream flow shoot up a bit, though it still doesn't go as high as I would expect necessarily. Particularly for that amount of rainfall. But I guess it might. This probably is also due to like soil moisture, and it's also here that having soil moisture data would be somewhat useful because probably this, even though this was a ton of rain within that hour or whatever, the soil might have been very dry, so it might have just absorbed it. So unlike say if there was that much rain in the winter. These are whole things we hope like our model can maybe learn just from seasonality and the temperature and stuff like that. So let's go. I'm gonna look at this. Let's look at actually some of when there's some of the max flows and stuff like that. Now, some of the max flow stuff. So df cfs dot max. So the max this ever hit was 6,140, which is actually probably pretty high. So we can look at this. Yeah, so, or wait, I'll just keep that there in case people want to see that. So yeah, the main reason I think that like here it didn't shoot up is if you look at the date in August, even though that's like, in theory, that's like a huge amount of precipitation. But the main reason I think is because it was probably August and this thing looks like it was, I think the surrounding soil was very dry. It also looks like if we look back at this data a bit, or the chart, it doesn't look like there were many ever. It would be good to see actually this, I'm going to go off of that for a sec. But it would be good to, I guess then I'll leave that, but it would be good to see maybe just percip because I can't tell anything about the axes. By the way, I definitely think there's a way to do the multiple things with different axes on each side. It's just, I think it's a more of a pain than it's worth at this point. Oh wait, that's like, oh, that's all the stuff. We want a DF percip sample. So yeah, it looks like, wait, actually that doesn't look right. Because didn't that thing say 30 or something? Yeah, I saw that said 30. 60,000, 50 free. 60,000, oh, 50 free. I think that would include it, right? What? The fuck? Okay, wait, that wasn't the right slice actually. My bad on that. That was the incorrect slice. You know, from now on I'm just gonna do like you'd think that like this would get us that exact row though, wouldn't you? Is this the right row? No, that's not the right row. What? That says 60,050 free. I don't know what's going on there. Do we need to, maybe I need to reset the index after dropping NA or some shit. Okay, so I was gonna go here now and figure this out. That should all be the same. It should just be the index that changes. They'll all run through this one just to make sure. So yeah, that's what happened. The index didn't reset. Now when we get that index though, I'm sure it should be correct. Okay, yeah. Wait, is that right? Okay, so yeah, that looks right. So yeah, that should be correct now. Now we can actually go and look at that. So we can do something like df percip sample. We'll just do like the 25 previous to it through there. So that's 28,000. 29,000. 9. Something like 9. Wait. 27,000. 9. 25 or something through. Or whatever. This should be good. Huh? How's that 0 fucking rows? Maybe I need to do iLock. Oh wait, no, that should just be df. No, yeah, it's df percip sample. Yeah, this is the correct one. Okay, so we should see the actual right stuff now. Yeah, so see that precipitation spike, the cubic footage goes a lot higher. Goes from all the way around 50 up past 250. That's still nowhere near 6,000 by the way, but which was the all-time high. But again, as I said before, this reasoning still pretty much applies. It's in August, so that's why the soil's probably dry. That's why it never really shoots up into the thousands range, I would guess. But yeah, there you have that like very extreme amount of precipitation and stuff like that. So anyway, so that's kind of some of the EDA there. From this we do see there's obviously definitely a correlation between the flow and the precipitation, etc. So hopefully our model can learn this. Though, as I said, this is going to be very much impacted, I think, by seasonality. So anyways, let's look at this. This here. Actually, let's look at this for a couple more seconds, too, and we can look at some of the lag per se. So this looks like this happens around time step. I know this is going to be borier now, but this will happen. The precip event we know happens right around a very extreme precipitation event happens right around time step. It looks like 28,000, and we don't really see the river rise till really rise a lot. I mean, it starts rising after it, probably like just a couple hours after it, but we don't see the max flow till like easily a bit more than 24-25 hours afterwards. So what I'm saying is probably in terms of parameters to set, say like the number of historical steps of say forecast history to pass into the model would probably be around I might go even all the way back to say 30 or 40 hours, maybe even more in terms of that. But you're never going to, for instance, probably want to have a forecast history of say less than 25 time steps passed into the model, or something like that, because otherwise you're not going to see the full effects of say the precipitation. So that's kind of where I'd start. I'd probably look at no less than that, if we can get anything out of this exploratory analysis when we go to forecast. So that's one. Now we'll explore a bit more about this. I'll just call this max CFS. And then what we can do with this is we can just do DF. DF CFS. Equals max CFS. Yeah. I mean, these would probably be good to be put into functions at some point. If I wasn't going to just use this for EDA, I would probably create functions that handled it, that handled this stuff. Like, basically got the max intervals and then plotted it and stuff. Actually, that would be a fun function to create, maybe. And it would also help to clean this up, probably. Yeah, I don't know. I only will probably be on an hour tonight, though. Anyway, so I guess no, let's create a function, because I have a feeling this could be useful for other streams. So we basically just do like def get max key or something. Get max range and then for some key or something. So the key would be like something the column name. I don't know what to call that. Just basically the column name, lower bound, upper bound. This will just be this stuff. Oh yeah, we always need to pass the stupid data frame to it. df, let's look at df column name. Okay, yeah, I'm getting ahead of myself there. This is going to look horrible. This is essentially like the equivalent of a messy SQL query, except with pandas. Does that even work? I'm going to check quickly see. I think you can call .index, right? Or wait, can I call .index on this? Or wait, no, I'd have to call it on that. Let me see that. Oh. I think you'd have to call 0 on that. Oh, we might have to call iloc actually. iloc.index or something. Wait, I need to get that. Pandas get indexed from row. That would probably be good. That iloc. Oh, index. Oh wait, df.index. Oh, you might call df.index. Wait, so I'd start with the index? That's maybe. Wait, is that in brackets or what is that in those? Okay, I think it's something like this. This should get me the index right. Kind of messy. I don't like doing that, but anyways, so this should just be .index .max. Oh yeah, this is going to be super long now. .toList. We're assuming there's only one of these two, but if it's max, I assume there's not anything identical right here, but so this is just going to be df.index. If I was using Flake, it would complain about the line length being too long here, probably. Okay, so that looks right. Then like the other thing we just do then is then do return, we could then do df, what is it? Index minus, I shouldn't call it bound, just like the lower number, upper number, index minus lower number. I'll just call it n, actually. I don't want to type that a lot. Upper n, lower n. To index plus. Okay, now we have a nice function that does this in not so shitty of a way. At least I think it does it. We'll try this. Column name, CFS 75. Yeah, we'll do 75 on each side. See what that returns. Nice, so that actually worked. Or I'm going to check and make sure it works actually. I thought the max CFS was something like 2,000 something. Wait, what is the max CFS? I just need. Wait, it's 6,140. It's probably in here that's there, I guess. Yeah, because it's on either side. So we'll plot that. Something like that. Ugh. Playbacks. So now what we do, we're just gonna do plot. Now we're gonna do plot. We'll look at just CFS now. This should reach somewhere. Yeah, so that reaches around 6,000 it looks like. So that we know that's correct. So I just want to see what. So it looks like it was in April, so it was already running high. Then my guess is then there was a precipitation event that drove it even higher. So DF max CFS PO1. Yeah, so then you got like all this precipitation. And that drove it way up to that. Okay, so that's some basic EDA stuff. I don't really. EDA is honestly kind of boring. But let's see. Or maybe actually do a plot with both of them. I'll see that. It will make the one thing look very small, but it might also be good. I really gotta figure out how to do different indices on both of these. I forget, do I have to do this inside again? Or I might have to. Oh wait, no, maybe not. No, it should just be that, right? How'd I do that before? I know I just did it before. Yeah, it was that. Oh wait, I didn't do this thing at the end. Okay, I need to figure out how to do the different indices because that just makes the precip look entirely flat, which we actually know it isn't. Different y-axis, plots with different scales. Okay, but I don't want to do that NumPy crap. It's this thing, I wonder if I can do that directly from pandas though, because I really don't want to like have to convert the shit to NumPy and shit. Oh, thank God for Stack Overflow. What? Okay, that's barely even worth it. Okay, I'll just use these separate plots. I'm honestly too lazy to work that other shit out to do them on the same plot right now. But as you can see, was it? Yeah, and again, I think you have that around 25-hour delay or so. Okay, yeah, this has been kind of boring, so, okay, that's some exploratory analysis. Really, nothing fancy here, just diving in, seeing how some of this works. Obviously, from this we can tell that seasonality is going to be a very core thing, because, like, what season it is going to probably make a lot of difference on the river height. As you can see, like this time in April, it was already kind of high due to snowpack, and then the precipitation caused it to go really higher, gain probably like 4,000, 5,000 cubic feet per second of discharge, and at least at the peak, whereas here back in August they only gained like 240, 250. I think a lot of that has to do to like soil moisture content, which we didn't have. So in any case, I think takeaways from this is we'll look about minimum 24, 25 hours of forecast history to pass into the model. That's another takeaway. I'll just fix up this stuff real quickly. So should move this function to the top. And we're just going to quickly move this function to the top, and then I'll probably run down through shit again. So here's our function. It's at the top. Easy to see. And then yeah, so anyway, so yeah, that's kind of the core of that. Yeah, I mean, if we were going to present some formal analysis, you might then go back and then like edit that notebook further. But instead, I'm going to, this time at least, I'll give you a preview of what we'll do. We'll work on actually creating a forecasting model, which will be in this second notebook. Not because I have any affinity to notebooks, but just because they're good, I think, at least on Kaggle for writing up a lot of results and stuff. So yeah, so we'll work on this in a bit. It's already kind of taking a while, so I'm not going to spend too much time on this, but moving towards how we'll actually use flow forecast, we'll obviously just install it, then we'll define very roughly install it. We'll still have to do some of that data manipulation ourselves to just drop the NA stuff. Then we'll define the hyperparameter sweep. Then train the model, and then do some like evolution stuff. That's kind of what it will look like. So So yeah, usually for this, I'll then create the def make config file. This will be the function that makes our configuration file. I won't do anything of that right now. Instead, I'll just kind of template it. But so yeah, that's kind of what's the idea of tonight's stream. And then as we move into tomorrow, we'll do another session where we'll, as I said, get right into the forecasting and things like that. So yeah, actually, probably for this I'll use an existing config file just because I don't like to rewrite them from scratch. But like for instance, we might use this configuration file, which was already used for training river forecasting models. But I'll go through each part of this and explain what each part of this configuration is doing, almost like I typed it up from scratch. And then yeah, we'll use this to start training the model and trying to forecast what the river is. So and yeah, it's pretty easy. Like as I said, this one's obviously one I used on river flow forecasting before. But say you had a sales or a revenue forecasting, it'd be just as easy to modify this as long as your data is already in one CSV at least to use this. Actually, I don't like this. I don't know why this is here. That shouldn't be there. To do that, and then here again is the swoop stuff. So yeah, well, it looks like actually one of my own recommendations, I think on my blog somewhere, was always start with DAR and N. So we will start with DAR and N in terms of forecasting, and then we'll move on from there to maybe some transformer models if that doesn't produce great results. But yeah, the idea of this too is then I'll also, once we do get a good model, I'll show you how to deploy it as well. We've really worked hard on creating some cool deployment interfaces recently. So it'll be an end-to-end thing where we'll go through stuff step by step until we find a good model, just like you would hopefully do on your actual data science problems and things like that. So that's kind of how it's going to work. I think probably altogether it might be 6 or 7 sessions or 8 sessions. But hopefully at the end it forms a kind of good cohesive end-to-end tutorial of how to use flow forecast for forecasting a data science problem. So that's kind of it for tonight though. Yeah, pretty much every night this week we'll spend, I guess, about an hour a night just doing this. So yeah, as always, if you have questions, you can if you have framework questions, questions about the framework specifically, then open an issue on GitHub. Just questions about this exercise you can put on YouTube or on Twitter. That's fine. So yeah, I hope everyone has a good night, and we will do some more of this kind of more of the actual fun stuff tomorrow in terms of the forecasting. So